Okay, so welcome back, everybody. Welcome back to AO3. Today, we are going to continue the discussion of the harmonic oscillators. And also, we will add damping force into the game and see what will happen. Okay? So this is actually what we have learned last time from this slide. We have analyzed the physics of a harmonic oscillator, so which we actually demonstrated last time, and you can see the device still there. And Hooke's law is actually far more general than what we saw before. It works for all small oscillations around about a point of equilibrium position. Okay, and that can be demonstrated by multiple different kind of physical systems. For example, here I have a mass which is actually can only move along this track here. And if I put this mass set free, and this thing is actually exercising harmonic oscillation. Okay? We can do this with large amplitude. We can also do it with small amplitude. And you see that, really, it works. Hooke's law actually works, and it predicts exactly the same motion as what you see on the slide. Okay? And we also have a little bit more complicated system. For example, this is actually some kind of rod, and you can actually fix one point and make it oscillate. And you see that, it also does some kind of harmonic oscillation. But now what is actually the oscillating is the amplitude. The amplitude is actually the angle with respect to the downward direction. And finally, this is actually the vertical version of this spring mass system, which you will be analyzing that in your PSET. And you see that, it actually oscillates up and down harmonically. So that's all very nice. And we also have learned one thing which is very, very interesting, is that a complex exponential is actually a pretty beautiful way to present the solution. And you will see it works also in describing the damped oscillators. And we will see how it works in the lecture today. I received several questions during my office hour and through email or Piazza. There were some confusions about doing a Taylor expansion. Okay, so in the lecture last time, the equilibrium position is at x equal to 0. Therefore, I do Taylor expansion around 0. Okay, but in this case, if the equilibrium position or the minima of the potential is at x equal to L, then what you need to do is to do a Taylor expansion around x equal to L, okay? Just to make that really, really clear, okay? Okay, I hope that will help you with the PSET question. Okay, so let's get started immediately. So let's continue the discussion of the equation of motion we arrived last time. So we have n x double dot, and this is equal to minus kx, okay? That is actually the formula from last time. And we can actually calculate the kinetic energy of this spring mass system. And basically, we will arrive, this is going to be equal to 1 over 2 m times x dot squared. Okay, and we can also calculate the potential energy of the spring. Potential energy. And that is equal to 1/2 kx squared. We also know what would be the total energy. The total energy will be a sum of the kinetic energy and the potential. basically you get this formula, 1/2 n x dot squared plus 1/2 k x squared. From last time, we have solved this equation of motion, right? So the solution we got is x equal to a cosine omega 0 t plus phi, while omega 0 is equal to square root of k over n. Therefore, we can actually calculate what would be the total energy as a function of time, right? So if we calculate that, you'll get E will be equal to 1/2 n a squared omega 0 squared sine squared omega 0 t plus phi. So this is actually the first term, okay, here, plus 1/2 k a squared cosine squared omega 0 t plus phi. Okay? And we also know that this term, this actually coefficient here is just ka squared, right? Because omega 0 is actually equal to square root of k over n. And if you replace this omega 0 square by k over n, then you actually arrive ka squared. Okay? So that is actually very good. So that means I can simplify the total energy. And what we are going to get is 1/2 ka squared. I can take this factor out. And that will give me, inside this bracket, I will get sine squared omega 0 t plus phi plus cosine squared omega 0 t plus phi. And this is actually equal to 1. Right? Just a reminder, sine squared theta plus cosine squared theta is always equal to 1. So that gives me this result. This is actually 1/2 ka squared. Okay, so that is actually the result. What does that mean? That means if I actually pull this mass harder, okay, so that initially it has larger amplitude, then the total energy is actually proportional to amplitude squared. Okay, so I am storing more and more energy if I increase the amplitude even more. Then I am storing the energy in this system, and it's proportional to a squared. And also, if the spring constant is larger, the same amplitude will give you more energy. So that means you can store more energy if you have larger spring constant. Okay. The most surprising thing is that actually, this is actually a constant, right? What does that mean? The total energy is actually not varying as a function of time. You see? So total energy is conserved, okay? So you can see from this slide, the total energy is actually shown as the sum, which is the green curve, and the kinetic energy and potential energy are shown as red and blue curves. Okay, you can see that their energy, the total energy is actually constant, but this system is very dynamical, you see? So the energy is actually going back and forth between the spring and the mass, okay? As in the form of kinetic energy and in the form of potential energy. But they are doing this so well such that the sum is actually a constant. So energy is actually conserved. Okay? So that is actually pretty beautiful and can be described very well by this mathematics. Any questions from here? Okay, so I would like to say simple harmonic motion. Actually, what you are going to get is the energy is actually conserved and independent of the time. And later, you will see an example with damping. And you will see that energy conservation is now no longer the case. Okay? So that's immediately jump to another example, which you say should be involving simple harmonic motion. So let's take this rod and nail system as an example. If I actually slightly move this rod, and then I release that, then you will you will see a simple harmonic motion, okay, also from this system. So that's actually do the calculation as another example. So this is actually my system. I have this rod, okay. Now I assume that the mass is actually uniformly distributed on this rod, and it's nailed on the wall, okay. And the length of this rod is actually L, so that means the center of mass is actually at L/2 with respect to the nail, okay. And also, this whole system is set up on Earth, right? Therefore, there will be gravitational force pointing downward, okay? So that means you have gravitational force Fg pointing downward, okay? So this is actually the system which I would like to understand. And just a reminder, what are we going to do afterward in order to turn the whole system into a language which we know describe the nature? What are we going to do? Anybody? We are going to define the coordinate system, right? So that I can translate everything into mathematics, right? So that's actually what we are always doing, and you will see that we are always doing this in this class. Okay, so what is actually the coordinate system which I would like to use? Since this system is going to be rotating back and forth, okay, therefore, I would like to define theta to be the angle with respect to an axis which is actually pointing downward, okay? So the origin of this coordinate system is theta equal to 0. This means that I'm pointing, the rod is actually pointing downward. Okay? And also, I need to define what is actually the positive, what is actually the positive value of the theta, right? So I define anti-clockwise direction to be positive, okay? So it is actually important to say, to actually first define that, then actually to translate everything into mathematics, okay? So the initial condition is the following. So I actually move this thing, rotate this thing slightly, then I actually release that really carefully without introducing any initial velocity, okay? Therefore, I have two initial conditions. Okay, at t equal to 0, there are two initial conditions. The first one is theta equal to theta 0 is equal to theta initial. The second condition is the same as what we have been doing last time. The initial velocity or angular velocity is actually equal to 0. So that gives you theta dot equal to 0. Okay? Now, we have actually defined the coordinate system. Then, now we can actually draw a force diagram, right? So that we can actually use our knowledge about the physics and to obtain the equation of motion, right? So now the force diagram looks like this. So this is actually the center of mass of this rod. And you have a force pointing downward, which is due to the gravitational force. Fg is equal to ng. Okay, it's pointing downward. Okay, the magnitude is actually equal to ng. And also, we know the r vector. This vector have a length of L over 2. Is pointing from the center of mass of this rod to the nail. Okay? And also, we know the angle between this vector pointing from the center of mass to the nail and the vertical direction, which we have already defined, which is actually called theta. Therefore, now we can actually calculate what will be the torque. Tau will be equal to this r vector cross the force, the total force acting on the center of mass. In this case, it's just Fg. Okay? So now we can actually write this down explicitly. Since the whole system is actually rotating on a single plane, right? So there's only one plane this rod is sitting on, and it's actually going back and forth only on this plane, okay? Therefore, actually, I can drop all the arrows and write it down, the magnitude of the tau directly, and this will be equal to minus ng L over 2 sine theta of t. Okay? Any questions so far? Okay. So now we have the torque, and we can make use rotational version of Newton's law to obtain the equation of motion, right? So that should be pretty straightforward. Tau will be equal to I, which is the moment of inertia of this system, and times alpha t. Okay? And just for your information, I already calculated the I for you. I is equal to 1/3 and L squared. Okay? So you can actually go back home and actually do a check to see if I am telling the truth. And if you trust me, and that's the answer, which is actually 1/3 and L squared if the mass is actually uniformly distributed on this rod. Okay? So that will give me minus NGL divided by 2 sine theta t. Okay, so that is actually coming from this side. Okay. So now I can actually simplify this expression. I can now plug in the I value into this equation, and I will get 1/3 and L squared theta double dot t, which is actually alpha. Okay, I now write it as a theta double dot, and that will be equal to minus NGL over 2 sine theta. Okay. I can move all the constants to the right-hand side. Therefore, I get theta double dot t. This is equal to minus NGL. Okay, actually, I can actually already simplify this, right? This actually cancel, and one of the L actually cancel. So therefore, I get minus 3g over 2 sine theta t. Okay, as usual, we actually define omega to replace this constant to make our life easier. So I can now define omega 0 equal to square root of 3g over 2L. Okay, and that will give you theta double dot of t equal to minus omega 0 squared sine theta t. Any questions so far? A lot of calculation, but actually all pretty straightforward. And actually, we are done. No? We are done because we have the equation of motion, and the rest of the job is to just solve it. So this is actually now the problem of the math department. So can anybody actually tell me the solution of the theta of t? Anybody?
Unfortunately, we have to approximate it.
Yeah, that's very unfortunate. So look, now we are facing a very difficult situation. We don't know how to solve this equation in front of you. I don't know, okay? Of course, you can actually solve it with a computer, okay? Or you want to go fancy, solve it with your cell phone if it doesn't explode. But it's not really nice to do this in front of you in a, you know, we don't learn too much, okay? So what are we going to do? So what we can do is actually to consider a special case. So we know that this equation of motion is exact, okay? So if you solve it, it will describe the motion of this rod, the motion of this thing, even with large angle, it works, okay? And now, in order to actually to show you the math in the class, therefore, actually, I will do a small approximation. So actually, I will only work on the case that when the amplitude is very small and see what is going to happen. So now I'm considering a special case. Up to now, everything is exact. And now I'm going to a special case. Theta of t goes to 0, okay? Then we can actually get this sine theta t is roughly theta t, okay? Based on the Taylor expansion, you can actually verify this, okay? So in this case, if we take theta equal to 1 degree, okay, then the ratio of the sine theta and the theta is actually equal to 99.99%, which is very good. If I take it as 5%, then I get at 5 degree, okay? And it's actually 99.9%. Even at 10 degree, okay, it's actually 99.5%. That shows you that sine theta is so close to theta, okay? We are pretty safe because the difference is smaller than 1%, okay? So that's very nice. After this approximation, okay, I get my final equation of motion, theta double dot t equal to minus omega 0 square theta t. Just a reminder, omega 0 is equal to square root of 3g over 2L. Okay? We have solved this equation in the last lecture, right? It's exactly the same, okay? Happen to be exactly the same. Therefore, I know the solution will be theta over t equal to a cosine omega 0 t plus phi. From the initial conditions, which I have 1 and 2, okay, I'm not going to go over this calculation again, but again, we can actually plug in 1 and 2 to solve the unknown a and phi. If you do this exercise, you will conclude that a is equal to theta initial, and phi is equal to 0. Okay? So what the full solution will be theta of t equal to a, okay, so a is now replaced by theta initial cosine omega 0 t. You can see that this actually works for this system. Simple harmonic oscillation actually describe this, the motion of this system as a function of time. You can also see a few more examples shown here. Two of them you are going to actually work on in your P set, and also another one involving circuit. If you have a capacitor and you have an inductor, actually the current, the size of the current is also doing a simple harmonic motion, okay? And as we actually discussed before, the energy is always conserved, and it's actually stored in different components of the systems, okay? So we have done this. What is actually new today? What we are going to do today is let's actually observe this phenomena here. So this thing is actually going to go back and forth, but it's actually not going to do that forever, right? Something is happening, which actually slow the motion down. I can also make use of this system, okay? I start from here, and I'm not worried that this actually goes out of this track, because I know for sure it will stop there. Why? Because the initial amplitude, okay, is not going to, okay, so the amplitude is not going to be larger than the initial amplitude, right? So I'm not worried at all, okay? But you can see that the amplitude is changing as a function of time. Apparently, something is missing, and that is actually a drag force or friction, which is actually not included in our calculation. So that actually try to make the calculation more realistic and see what is going to happen. So now I will introduce a drag force, okay, which actually introduce a torque tau drag T, which is equal to minus B. B is actually some kind of constant, which is given to you. Theta dot T, which is actually proportional to the angular velocity of that rod, okay? And also, of course, I keep the original approximation. The theta is very small, such that I don't have to deal with the integration of sine theta, okay? So solving this theta double dot equal to minus omega 0 squared sine theta, this complicated function, okay? You may ask, why do I actually introduce a drag force proportional to the velocity? Okay, and why do we put a minus sign there? Okay, that is actually because if you have a minus sign, okay, that means when this mass or that rod is actually, for example, it's actually going downward, then the drag force is really dragging it because it's actually in the opposite direction of the velocity of the mass or the angular velocity of the rod, okay? So I need a minus sign there, okay? Otherwise, it's not a drag force anymore. It's actually accelerating the whole thing, okay? Secondly, why do I choose that to be proportional to theta dot or velocity, okay? There's really no much deeper reason. I choose this form because I can actually solve it in front of you. Okay, the reality is actually between proportional to theta dot and the theta dot square, for example. Okay, this is actually a model which I introduced here, which I can actually solve it in front of you. Okay. On the other hand, you will see that it's actually not bad at all. Okay, it actually works and describe the system which we actually will perform the demo here. Okay, And once we have introduced this, okay, the equation of motion will be modified. Okay, so let's come back to the equation of motion. So you have theta double dot t originally will be equal to tau total t divided by I. Okay, and now this will become tau t plus tau drag. T divided by I. There's additional term here. Okay, if I simplify this whole equation, then I get minus ng L over 2, okay, sines theta, and this is actually roughly theta, okay, minus b theta dot divided by 1/3 of ml squared. Okay, so you can see that I still make this approximation sin theta roughly equal to theta. Okay, then I can actually arrive this equation in a small angle case. Okay, I get minus 3g over 2l theta t minus 3b over ml squared theta dot t. Okay, and now as usual, I define omega 0 squared equal to 3g over 2l, and I can also define gamma is equal to 3b over ml squared. Okay, just to make my life easier, right? Finally, we will arrive this expression, theta double dot plus gamma theta dot plus omega 0 squared theta, and that is equal to 0. So what you can see from here is that we have actually arrived and derived the equation of motion. Okay, we have derived the equation of motion, and what is actually the rest part of the work is actually really just solve this equation of motion. And you don't really have to solve it because you already get the result from 1803 actually, if you remember. And we are going to discuss the result. But before that, before I really try to solve this equation, I would like to take a vote. Okay, so here I have two systems. Okay, they have equal amount of mass. Okay, they are attached to a spring. Okay, if you do the same equation of motion derivation, you will actually get exactly the same solution. Exactly the same equation of motion in that format. Okay, so the form of the equation of motion will be the same between this system and that system. Okay.